document camera on screen. And we should be recording. We'll hope our fourth day with our fourth setup we'll finally let the sound get recorded on these. It's definitely it's fun teaching a class the first time. Teaching it the second time is not as fun, particularly to an empty room. All right. So the last time that we met, we were talking over FETs, and we did a basic what's called static CMOS design. There's one name for it. It sometimes also goes by pull up and pull down networks. There's a couple different names that it can be used. It's kind of your basic static CMOS situation. And we call it static basically because we have, if you remember, we have a pull up network. Basically, these are the ones that were supplying power from whatever your, VDD. And then you had your function output. And then you had a pull down network that was hooked to ground. And basically you had all your inputs set to each of these different networks that allowed you to define them. And we could do either one of these networks, and we got the other one by basically flipping it. All right, we had to, whatever was parallel became series, and series became parallel. So we were able to do that kind of basic switching. And we call it static because it's basically good to read all the time. Right? As soon as something switches, it updates, it's powered, it's reasonably fast on here. So it's the static part, though, is particularly important because it's after a short transition period from one value to the next when you change your inputs, it's going to stay at that level. And the disadvantages that this type of a network or static design has, number one is these can be a little bit complicated and stuff, but it's not that bad. You have to generate two of them. The big part is actually an issue of speed. They're not bad, but they're not like super, super fast. So we're going to talk about two different major kind of categories today. One is going to be another static design technique called transmission gates. And basically the idea of a transition gate is they're really good in certain cases. It's designed to just be a very elegant way, particularly to do muxes. But it's basically allows you to, it's kind of like a nice analog switch that we can then turn into logic. So we have this one under static. So we're going to have two different categories. Static, we did this one last time. We're going to add in transmissions gates. All right, so this will be one thing we'll talk about today. And then we'll talk about dynamic, which will be our other big area. And under these, we're going to have precharge-excites or executes. And then we'll talk about domino. The neat thing about the dynamic ones is they're in general about maybe twice as fast to run as a standard static one. Sometimes they get better power, sometimes they get worse power. That can actually trade off, and it'll depend on some of the situations for how what your signal looks like and things of that sort. But generally, if you're going to dynamic, your big issue is you want a very, very fast system. Speed is your issue here. So domino logic, for instance, is probably the major general family that's out there when people are building chips. When you're designing a computer and stuff, the majority of your logic is going to be in domino logic because that allows you to get the really fast gating that we want. As a matter of fact, it requires you to have fast gating. There's actually a minimum clocking time that you end up with domino. it really wants you to go very, very fast. And yes, it is actually named after dominoes knocking things down. But the pre-charge actually will give you domino as a neat little effect. So domino is going to be a variant of this, really, but a very important one. All right. So this is kind of, for the CMOS style logic, this is kind of the map of what it is. These are two big static families. There's actually a whole bunch of ones out there, but these ones will give you the basic flavor of how static design is. And then a basic look into dynamic circuits for speed. All right. That's kind of my roadmap, particularly for today. Let me get this pens out of the way. All right. So actually, let me, before we go on to the next thing, let me just make one little commentary about each of these, right? When you're doing these, right, designing these networks, because you might be wondering, okay, how would I go about doing it? We've shown you how to analyze them. A decent amount, you'll do more analysis than you'll do design in general. Because a lot of times there's something existing and you've got to use it, and sometimes, you know, it's not particularly well documented, or you want to verify it, or you want to write an analysis for it. So you have to be able to look at the circuit and figure out what's going on. Particularly when you're going in and testing something else, I often tell people you should never simulate something unless you already know the answer. And just think about that for 1 second, because it almost sounds contradictory, right? If you already know the answer, why simulate it? But the reason why I say that is you should know the answer because you should know the basic answer. You're not going to necessarily know all the details, the exact voltage, but you ought to be able to look at the circuit, do enough analysis that you know what you're expecting to see out of this circuit. Because otherwise, what good does it do you? If you don't know what you're expecting out of this circuit, you know, whatever answer the simulation gives you is the law to you. But what if somebody made the simulation wrong? Or what if there's actually an error in the simulation? It does happen. Right? How would you be able to evaluate this? So that's why I say you should understand basically how the circuit works. And then when you take a look at your simulation, you're going to want to look at that and say, does this make sense? Does it not make sense? So that's one cut on that whole situation. Now, there is a chance you might get into doing this, in which case you'll need a whole nother course, VLSI, but this will give you, basically we're in 2 weeks giving you an overview of VLSI techniques, why they work and how they work. And then we're just going to use them. But I feel you should at least be conversationally understanding and able to look at a circuit and understand the basic techniques of how VLSI is done. Even if you're not going to do it. It's a select group of people who are going to fabricate the chips. But everybody should understand it. And it kind of just comes down to you're a better driver if you understand your car. At least from my perspective. Now, the neat thing is when you're actually doing these designs, you can do these designs here, for instance, with K-maps. And we'll actually do, when we get to these pre-charge and then evaluate systems, we'll do one with using a K-map to do the design off of it. And obviously, you could use any other logic style you want. Transmission gates are really particularly good with Mux design technique, which, if you remember from your digital logic, is a particularly easy and elegant technique. And that's really why the transmission gates are very nice to use, because they're really good for building on one of the easiest, most elegant design techniques that's out there. That's just kind of a commentary on them. All right. So let's start off with transmission gates. Think for a sec. What type of MOS is this? Is this N or P? P. Yeah. This is a PMOS, right? Remember two ways you can think of this. The technical reason is, what is the actual channel you have to create to connect them up? And it's a P channel. You have to induce which means you have to put minus charge on the other side of the capacitor to induce the positive charges. Okay? And what does this carry voltage or ground better? Carries voltage better. Why? Think back for a sec. We want to kind of induce that channel here. That's the P channel from which the name comes. And then we've got our silicon dioxide layer. And then, you know, a metal or a polysilicide most likely, right? That's connected. Now, what we want to be able to do is put a whole bunch of minuses here so that we can induce the pluses here. And remember, we're going to take these two, and we usually just kind of hook them together. So, you know, the wire coming off, we've kind of hooked it into the backplane area so that there's establishment. There's a couple ways you could do it. You could hook it here and then into the underlying undoped, and then this one is coming off. Okay? So that's kind of the basic setup that you're doing. If you remember, the similar type of thing we were doing with BJTs, right? But on the P types, we always do it towards the reference, your higher voltage side. So this is usually a really high voltage relative in the system. And this one, in order to get all these minuses here, has to be low. All right. So if I'm carrying something through here, and this is really high, I'm carrying voltage, right? That's what I'm trying to pass through. Then I'm exactly set up for what I want. This one has to be higher than that one. If you're passing high voltage, it's going to be really efficient because you're going to hook high voltage up here. And it'll pass it through because that's exactly what it's expecting in order to induce it. What if I violate this assumption and I make this low voltage? Right? I'm trying to pass low voltage through. Right? This is the question. Right? It obviously does well at high because that's exactly what it's built for. What happens if what I'm hooking is low and I'm trying to pass it through from this side to that? Well, this has to be lower than that. So this has to be really, really low. Right? But I can only get down to ground, which means this can't go super low. This is going to have to stay above it by at least several tenths, right? If somewhere in the high tenths up to a volt. Right? This has to be higher than that. It just has to. Otherwise the gate doesn't open. So can this pass low? No, it can't pass super low because this side to go over to this side, I have to have that channel, so this has to be lower. It won't work. So this, my PMOS, will not do a good job on passing. Does that make sense? Okay. This becomes really important for transmission gates, so that's why I'm just kind of reviewing it. So imagine I had this, and imagine I didn't overdraw my lines, but sloppy, whatever. Okay. What's that? NMOS. What does it do a good job passing? Passing ground. Why won't it pass power well?
You need to have the gate higher than the power.
Yeah. Right. Imagine we just flipped all these, right? I want minuses here. Here's my silicon dioxide. Here's my polysilicide. All right. We now connect this side, which is expected to be low. This has to become high relative to it in order to get my positives here. All right. So as long as I'm passing low, I can easily make this higher than that. That's very simple, so it does a great job passing low. Make sense? What happens when this becomes high? Well, this has to become really, really high. But it can only get up to whatever your maximum thing is, whatever that is, 3.3 volts, 5 volts, whatever, which means this has to be lower than that by enough to activate the gate. So you can't pass the highest voltage because the gate won't turn on to do it. Does that make sense? Right? A very similar argument can be done with BJTs. Right? This is why you need both sides. One passes power, the other passes ground. Could you do it? Yes, but you're going to lose efficiency on whichever end it's not good at. All right? But what if I wanted to pass the signal perfectly? Well, I'd have to take these and kind of, flip them around. So I could do, this one passes this direction really nicely because that's the side that's hooked. So that one goes this way. This one is kind of trying to go that way. So we usually flip this one onto the bottom because we just rotate it around. So you'll often see these drawn. There's a couple ways you can do them. One is like this, because then it'll pass this direction, left, right. Technically it should. If you remove this so it doesn't bias the bottom, then they're bidirectional. So we'll often break this to the bottom to remove that, the problem. So it is a true bidirectional gate. If I do it like this, it's not necessarily bidirectional. It usually does have a direction for this version. If I break it and it's bidirectional, we usually use what's called a bow tie to symbolize that. And there's two ways that can be drawn. This is your basic bow tie, and you'll put the negative one of the gate on one side. So you have this version. That's kind of the simplified one, and it's not guaranteed. It might only be one of the two gates if you do it that way. Not perfectly bidirectional. This is the preferred method if you've made a true, awesome bidirectional gate. The double bow tie. So when it's really, truly bidirectional, I would suggest the double bow tie. That's going to be well understood. I have seen people do this in exchange for it. It's not quite as clear, so it is better to use this one. This one we often use in a lot of logic builds because we really do have kind of a direction in mind. Even if it is bidirectional, we'll often draw it this way, just on logic, because we do want you to think of it as passing in a particular direction. Although you can do either one. And this is just the two ones just flipped around and pushed together. So you can kind of think of this as a wire, and you can see one FET, and you can see the other FET, and then wire coming out. So this is kind of the symbols we'll use to draw them. This is guaranteed, analog or pretty much anywhere for true bidirectional. This one is often in logic, and this one's a special variant. Does it make sense symbolically what it is and how it works? All right. So let's think for each one of these, right? I've got two halves. I'm just going to go in here because I think it lets you see what's happening for each one. So I want you to think for a sec. We've got a selection here. And let's imagine this select is S on this top port. And I've got some A going to B. Okay. A, B, I've got my select. And we'll figure out what we want to do with this one here in a sec. Just imagine this select right here. And A can either be 0 or 1. And it'll matter whether select is 0 or 1. Now, when does this top gate, right, this one here, when does this one allow me to transfer? When S is 0 or 1. So if this S here is 0, like having a 0 here, will this gate be on or off? It will be off, right? So it won't transfer. So when S is 0, it's off. And this gate transfers what? Ground or voltage? Ground. So this one right here, it's transferring ground, 0, but it's off. So we get kind of a Z here. What happens to this gate when S is a 1? It'll do a great job transferring that 0. Do we agree? It doesn't do a great job with the 1, though. Now, when does this gate turn on, right? This lower part. When its input is high or low? Low. And we'd really kind of like it to go at the same time. I'd like this one to go when S is high, but it wants to go when it's low. So what do I have to do?
Have a relatively high signal, like a signal that's high relative to the S value.
Okay, so I could just, so I'd have to boost the voltage at that point, but then I'm going to require more voltage. And what happens if you ever get a connection? It could potentially short, right? So it is a clever idea, right? I could do a voltage shifting, and sometimes that's a good way to go, right? But it does have some dangers. Right? And if I boost it high enough that a 0 is on, what will happen with a 1? Yeah, so I could shift things around, but it'll stop doing my kind of flipping thing. I really want this one to be off when it's low and on when it's high. The exact opposite of what it does. So is there a way I can modify this? You can invert the input. So we put S bar here. And we're just going to specify you need to do this. It must be S bar. Because we want both gates on at the same time. That's the whole point of this. We're only giving you both gates, so one carries power well, one carries ground well. So you get a really good transmission of the two. So you have to invert them. It goes so far that on some of these, they'll actually, instead of giving you both controls, they'll just hook an inverter there and only give you one. Right? Now, that's not ideal because sometimes there's ways you might have both the signal and its inverse already there, and so you save space if you don't put the inverter in. Right? And there are a lot of times we have both. So think like, for instance, on a flip-flop, you have both available to you. So why get an inverter? Just grab it from its appropriate areas. Okay, so we're going to do S bar, which means this one, since it's S bar, when S is high, it will also be on. And it does a great job transmitting the 1. And when S is low, S bar is high, so that gate is off, so it doesn't transmit anything. That make sense? So we now have a transmission gate, such that as long as you make this S and S bar on the dotted side, we now have, when S is low, it shuts off, and when S is high, it just passes through. And it'll pass through, since both of them are pretty optimized, it'll pass through really well. You will not get much of a drop. It doesn't weaken the signal a lot. So you can pass quite a few of these through cascaded. Now, obviously, nothing is going to pass forever, right? The longer you go down a channel, the weaker a signal is going to get. So eventually, you're going to have to boost the signal. And that's just required by this. After so many stages, boosting it will be required. But you could just put in a simple buffer, right? Or you could switch to negative logic and just put an inverter, which is 2 transmission gates, and it'll be fully powered again, a new signal. So there's a couple ways we can do this. That's can make it very easy. But ideally, this is going to power it. It'll be a little bit weaker, but not much. But it's now a nice, easy way to go. So far, so good? So think about this. This setup is basically kind of like the tri-state gates we've talked about, except tri-state gates are not, they don't pass things quite as well as this does. Really, this is just an upgraded performance on tri-state gate. And tri-state gates are really good for building muxes. So these should be really good for building muxes. So let's consider our ideal situation, a mux here. Now, a mux, we have a control signal which is either 0 or 1. And usually, right, so let's just kind of get a standard mux symbol, 0, 1. We have 2 inputs and an output. All right, so I have A, B, and C. And your mux has some control S. So our truth table for this is, we have S, and we have A, B, or they don't need a lot of room. I'm not going to write out what these are. C, when S is 0, C gets the value of A, whatever it is, all right, because that's what's been hooked up. And when S is 1, C gets the value of B. And we don't really care what they are, it just passes them through. That's why I say I can fit pretty small. Because it doesn't matter whether A or B is 0 or 1. Whatever it is goes through. That make sense? So let's think about how we can do this. How could I pass, let's do the easy one. How can I pass B to C using a transmission gate?
Same bidirectional gate.
Yeah, we can just take directly our gate. And I want to have S coming in. And I have S bar, which I can get S bar by just putting it into a notch or taking it from wherever. I'm just going to write the S bar for cleanness here. And I just hook my B here. And I hook it out to C. That's going to do this whole lower part here, right? And when S is 0, right, when I want A to come through, S is 0, this doesn't contribute anything. It's completely disconnected, so it does nothing. It's like a pulled wire. It's an open circuit. So it's irrelevant that it's there. So how could I do my second part of this circuit, this upper one? S is 0, I get A. Yeah, consider I take this same circuit and now I hook it this way. Now when S is 0, this is open, S bar is 1. All right? So this gate opens when S is 0 and lets A through. And it builds that part of the table. And when S goes high, S bar goes low, and this whole gate is turned off. So it's high impedance and it's ignored. This one passes one part of the table, this passes the other. That make sense? So it's true. I mean, that's a mux right there. I'm able to build a mux with 4 gates. If you want the inverter for S in addition, because you don't have S available, sometimes you do, so you can get away with 4. If you need it, an inverter is only 2 gates. That's how we were able to build it with our static logic. That's trivial. So I can build this with either 4 or 6 gates, depending on whether S bar is also available. All right, for a mux, that's a pretty nice result if you think about it. Space-wise, that's really efficient. And I get really good transmission of the signal, and I can use a mux design. And once I have a 2-input mux, right, this is an if statement in Verilog. I can implement an if statement with 4 transistors. And if I want more, I can just cascade them. It's a binary tree. So you just build your binary tree, you build it as big as you want. Huh? So if I want to do 2 of these, I'll need 2 levels of the selection, and then another one to select between them. So I'll need 3 to get 2 levels of this setup. But that still means to handle 2 of them, I only need 12 transistors. Again, very, very efficient. It would be very hard to build something this efficient in some other logic form. So that's where this one kind of really shines. And now you can do everything you did before with Mux Design. So just a refresher, does everybody remember how Mux Design works? Some yeses. Say no if you don't remember, right? Because otherwise this technique is not as hugely cool, right? This is hugely cool because Mux technique is really elegant. Let's just do something kind of quick. We could build this. We believe we can build even bigger gates from here. So imagine for a sec, let me just, let's say we just had a table that looked like A, B, and I wanted 0, 0, 0, 1. And let's say I wanted 1, 0, 1, 1. Right? Fair enough? So those who said they remember Mux techniques, do you remember what the basic thing I have to do for Mux? We break them into row groups of 2. We're going to separate off our least significant signal, B. And we're going to then say, okay, this happens when A is equal to 0. This happens when A is equal to 1. That's kind of the groupings of them. And then I look at my output F compared to B. And I notice this is 1, 0, and this is 0, 1. So that means my output F for this is B bar. Right? The negation of B. And for this row, my output is 1. Doesn't matter what B is. So I could get all possible combinations of 2 inputs, right? If they're both 0, it's 0, right? If it's 0, 1, then it's the same as B. And you just walk down in each of these 2 groups and you just say, is it the opposite of B? Is it always 1? Is it 0? So it's real trivial. You just kind of group them up and you walk down. This, everything from this side over is your selector. So I hook this to S. So on our previous signal, right, A is equal to S. So when you're doing here, right, we saw how the gate works, we built it. So my S is just, I hook to my signal A from this. Now my input A here, so I'm just going to do this simpler drawing because it's a lot faster. Is that good? So I can hook my A up here to the select switch. Which remember, this picture right here is identical. Try to get them all on the same page at the same time. Right? This picture, right? These inputs, S, output, is identical to this, right? S, the S bars. So it doesn't matter which of these we draw, right? So I use this as my selector, right? It tells me, am I in the 0, 1 or the 1? 0 or 1. When select is 0, I want to pass through B prime. Well, it passes this one through, so I put B there, or B bar. B bar, B prime, whichever you like to call it. Right, the negation of B. On the other one, when the selector is 1, I need to pass a 1 through, so I just give it power. And this is now my function F. Done. Okay. This technique is like really, if you get the bigger ones, right? A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. All right. You guys pick something. Some pattern of zeros and ones, just so you know I'm not cheating.
1 1 0 0 1 1 1 0.
You like it? Fair enough? Is that good? Okay, so we're going to follow our thing. We group them up 2 at a time. We cut off the least significant bit. This is now my address, 0, 0, right? It's just a 2-stage. This is both 0, 1, 1, 0, 1, 1. Okay. This is just a 4-input mux. And a 4-input mux, all I have to do is take a 2-input mux, a second 2-input mux, and I hook this one to the least significant bit, and then they come into another, and I hook this to the most significant bit. I have my function out, and I have this is select the 0 and the 0 line, right? So on and so forth. So this is the least significant bit, the most significant bit. And so I have the input. This is 0, 0, 1, sorry, 0, 1, 1, 0, and 1, 1. That's the address here, and I want to just hook up whatever the function is there to get the output. All right, so this becomes, in essence, a symbol for a much bigger gate, where these 2 bits just come out. We'll just group them together into a 2-bit address. All right, and these are just what you built before. We just cascade them. Remember I said it's just a binary tree. And then I'm able to get, these are just the address lines. This is the 0 input, the 1 input, the 2 input, the 3 input. Because the address line, to get this one right here, the 1, 0, you have to send a 1 here and a 0 to here. So if you pick the most significant bit is 1 and the least significant bit is 0, it'll open this pathway here through. And so whatever you put on this line will go through when the address says 1, 0. So this, in essence, just becomes 0, 1, 2, 3. 0, 1, 2, 3. And you have your select, which is now 2 bits. You have your function coming out, and you have your 4 inputs. But I could just build that out of my transmission gates because this, right, I break this down into this, and each of those is one of these, which is just made of 2 transmission gates. Right, so this is a total of 6 transmission gates. Done. Make sense? So we could build these, we could build the muxes as big as we want. I just want you to realize once I've built a 2-input mux to you, you can make as big of a mux as you want. Remember in Verilog, right, a 2-input mux is an if statement. So anytime you write an if statement, that's what you're getting. Right? But I can also build any other logic gate you want. If you want this, this is just a nested if. An if inside another if. Right? This one is if, right, the most significant bit, then this, else this. The 0 is the else clause, the 1 is the then clause. You can think of it in that way too, and you can nest them. But you nest a whole bunch of these, and these also become a case statement. So if you build a case statement or a bunch of nested if-thens, it's going to be transmission gates very efficiently. And remember, that was really common for us. So transmission gates really have a very good place on implementing a lot of our hardware code. But anyway, just to finish this one off and show you what you do here, right? We grouped them up. I'm just going to take a look at these and compare them to C. These are both 1s, so I'm going to put a 1 on that input. These are both 0s, so I'm going to put a 0 on the input for 0, 1. These are both 1s again, so I'm going to put a 1 on 1, 0, or 2's input. 1, 0 is the flip of this, so that's C bar. So I'm going to put a C bar on 1, 1, or 3's. There you go. Instant gate built to implement that logic function you came up randomly. We did that in like 2-3 minutes with me making commentary. Okay? See how elegant it is once you have these transmission gates? It's a surprisingly neat technique. All right. Let me give you one other. There's also some fun stuff you can do with transmission gates if you like playing little elegant games. I consider these kind of like mathematically fun games. But let's do the kind of simplest one you can imagine. Imagine I took one of my gates, and let's say I'm going to guarantee, I'm going to just draw in the inverter explicitly. Just so we definitely have it placed here. All right? So I've got that input and I've got this input. And then imagine on my output here, I'm just going to put some resistor to ground. All right? This is called a pull down resistor. Okay, and let me just call this A and call this B, and I want to ask what's F. Now notice, I'm not powering this by straight power and ground anymore. I'm powering it by some signal. That's no problem, it's a select. So let's consider A, B, and what it's going to do for F. Now, A is kind of functioning like select. All right? So we've got A, 2 zeros, 2 1s. And B. So since A is basically my select, if A is equal to 1, this is open. Do we agree? Yes. Okay. Everybody's nodding yes, it looks like. All right. So that means B goes through. So if A is 1, B goes through. This is nothing different than we've already said on the basic behavior on it. And when A is 0, it doesn't go through. Do we agree? Which means this is disconnected. So what happens to the circuit? It's not Z anymore because I got that pull down resistor. So that pull down resistor, there's not going to be a lot of current to flow through this, right? Once it's pulled through, that's just a path to drain any charge. So if it was high, it'll pull it down. All right. And once it's pulled it down, there's no more current flowing, so power stops flowing. End of story. Right. So that's kind of a draining path. But if you're trying to send a 1 out, the resistor will keep it. All right. So that means this has to be a 0 because that's off. What's that gate? It's an AND gate. So I now just built an AND gate with 2 transistors and a resistor. Kind of a fairly nice, elegant system for it. Oh. And if you notice, when I was doing the design analysis, I broke it into the same way. Right? This is also very popular for like XORs or equivalent circuits because you can kind of break them up into these type of patterns. But basically, that's the trick to how all of these work. If I wanted to make an OR you can imagine an OR looks like, I drew that backwards. 0, 1, 1, 1. Right, that's an OR. You could break it into pieces. I go, oh, I want to pass through B on that, so I can just flip A. Right, and then it'll pass B through. So if I put A bar in instead of A, I just put an extra NOT gate there, or flip the NOT gate to the other side if you want to think of it that way. That would let me pass this one through, and then I put a pull up resistor. An instant OR gate. You see, it's really kind of easy to build just straight logic too. So I don't just have to build muxes. I can go through and build logic functions from here. All right. So these gates are kind of, I kind of view these are kind of like fun engineering puzzles. It's kind of like, ooh, can I come up with a clever way of opening and closing? And it basically is passing two values at once. So you kind of get this nice breakup of how the circuit goes. And then it's just at that point, it's all elegance. You know, it's like puzzle piece fitting. So this is kind of as close as we get to playing with puzzles. But you can get some really, maybe you think about it, I can build an AND or an OR gate, right, with again, like 2 to 4 transistors. That's extremely elegant. Right, very low power transfer, away I go. All right, do we feel good? Okay. That gives you the idea of transmission gates and kind of how can I use them nice and effectively. Yeah. Let's get dirt on the paper. I nearly stepped on that. Okay. Let's start talking about dynamic logic. Right? So to think about this, we've talked a little bit about time, but let me get a little more quantitative because I want to show you one of our two gates is slower than the other. So remember, on any of our FET designs, it's basically centered around a capacitor. What's the equation of a capacitor? CV equals Q, right? You agree? What happens if I take the time derivative of this? Right? Well, if I get the time derivative, the derivative of Q is I, your current. All right? And I get C, assume your capacitance isn't changing. And then I'm going to get the change in V or the change in time. I'm going to kind of write it this way because I'm going to split my derivative up here and solve it. All right? So I'm going to take time to the other side. Turn over I, V. So this is telling you the time it's going to take to charge or discharge that capacitor should basically be proportional to the C over I times delta V. C over I is sometimes what we call logical effort. Right? For your particular family, how much, actual effort, how much does the circuit have to put into it to do it? So, you basically have a capacitance designed for your family. How much current do you have? All right? This is the voltage swing for whatever your system is on, right? 3.35, whatever. All right? If I want this delta T, right, which is kind of the delay, how long it's going to take me to charge or discharge that capacitor, which is how fast I can turn on or off the switch. I want that delta T to be small, right? So what happens as the capacitance gets big? The time gets big. So I want a very small capacitance. What do I want with I? I would like I to be big, right? And if you think about it, you're trying to get charges there. So the more charge I give you in a period of time, the faster you're going to turn that gate on. Now that's going to cost you some heat, but it tells you a basic reality. If you want to turn a gate on or off, you are going to have to give some current to us. Right? There's just no two ways about it. So bigger current is better, right? Smaller capacitance is better. And how about voltage swing? Smaller voltage swing is better. Anybody notice the voltages on logic? Well, they keep getting smaller and smaller and smaller. It was 5 volts back in like the 70s and 80s, the good old days, right? And, you know, as we moved up, we moved to 3.3 and then 1.8, and right, it's getting smaller and smaller. One is due to power, but the other is it actually makes it faster. The current, I'd like to give it as much as I can. So to compare the actual logic variance of the capacitance becomes important between them. Okay? And it's going to be this term that's going to matter to us here for a second. So let's just consider our 2 basic ones. This one was what type of gate? NMOS, right? And what's the carrier in the channel if it's NMOS? It's electrons, right? So if I want, remember again, we have our conduction band and our valence band. We got our Fermi energy in between. Basically, what I want is an electron to get promoted and it moves about the country, right? That's the basic requirement for movement. It just gets promoted and off it goes. Now, how about the charge carrier for my PMOS? Valence, conduction, and for my hole to move, it's got to go up, and it moves over to the next one and pops down. And then it's got to pop up and move over and pop down. That's how holes move, right? So this one has a much more difficult path, and it's got a bigger jump here too. So what would you expect speed-wise between how fast the carriers will move here compared to here? This should be a little faster, right? That should be slower. And it's slower, so it means it carries less current, right? This is charges. This is going to take more time, so charge per time, right? My current, this is going to have less current because your time has increased. And I is Q per time. Okay? So this one takes more time. All right? So in order to get the same amount of current, that means I've got to build, this takes roughly 3 times as long, which means you're going to get 1/3 the current. So to get the same current, because I need to keep my current the same, you're going to have to make it 3 times as big. So roughly speaking, when you're building these PMOS ones, they are 3 times as big and roughly 3 times the amount of capacitance of the NMOS. Okay? They're slower, they're bigger, right? Everything you hate. Right? I mean, that's the basic problem that we have. It's 3 times as big. There's no 2 ways about it. And therefore, it causes me lots of problems. It's slower and it's bigger. And the second it gets bigger, away you go. And so pound for pound, there's no way to avoid it. Triple the size and triple, the delay. So if you could get rid of one, you want to get rid of the P's. But the P's switch which? Power or ground? Power. So what that means is on my original static circuit, this is 3 times the size and 1/3 my speed. Right? Everything bad lives up here. That's kind of nice. As an engineer, what does that mean you want to do? Yeah, get rid of it. Right? I want to optimize this whole circuit. I would like to get rid of my pull-up network. Just make it go away. Because if I do, it's going to get rid of my biggest space area, and it's going to speed my whole design up. Faster, smaller. These are good things. Right? We just have to get rid of this. Right? And if you remember, for every input, there's roughly one transistor. So if I have n inputs, there's n transistors up here, n transistors down there. Right? And this is 3/4 of my area. So if I can get rid of this, it'll be fast and small. Right there, that observation is completely the idea behind dynamic logic. Get rid of the pull-up network. Right? Now, the only problem with this is that your pull-up network supplies power. How do you get power otherwise? So we're going to walk through what's the basic argument. So this whole thing is just to motivate, why do I want to get rid of the pull-up network? Now let's see what we can do to get rid of that pull-up network. So consider for a sec, I'm going to just do this big block, right? My pull-down network. We like this one, right? We've got its inputs. And right now we're just going to say, hook this to ground. Now, I need something that's going to be able to handle this. Now, this pull-down network supplies all the zeros. So if you're thinking, remember we said you can kind of build these with Carnot maps? Right? If you do Carnot maps and you do encirclements of zeros, right, that's where they come from, is right here. So whenever this pull-down network, a gate opens up, right? Any of the thing inside the encirclements, it'll ground things for you. So I would like to take this, right? If I know the zeros, as long as I got something that's going to force the power in the other spots, then I'm okay. Does that make sense? Well, if I don't want to have a direct connection to power while I'm doing calculation, then what can I do instead? What else can give me power besides a hookup to power? A capacitor could, right? What if I had a capacitor here on the output? And say, for instance, this capacitor was charged. We'll figure out how to get it charged in a second. But let's just assume it's charged for the moment. So if this is charged, and this says, okay, hook me to ground, give me a 0, that capacitor will discharge and you'll get a 0, right? And if this network does not turn on, then what's going to happen? This will not be there, and you'll see the charge from the capacitor. Now that capacitor will slowly discharge as it goes out to your system. So you're going to have to refresh this capacitor. This is why I say there's a minimum time, and that time is the time between recharging these. Okay? But that right there is the basic idea. Right? This is the center of it. Now we have to build something that's going to get the charge on here. All right? But I can't really disconnect this, can I? Because that's what you'd like to do. Right? Charge it up, hook it in. Right? Or ideally have something that's just always supplying you that. But that's kind of dangerous. Okay? So what we're going to do is we're going to come in here and we're going to put on a clock circuit that's going to turn on a charging circuit. And when the charging circuit's on, we're going to want this one off. All right, so that's going to be what's called our pre-charge stage. And then we're going to, once it's done charging it, we're going to switch over and evaluate your logic. So we're going to have two kind of stages. We'll have a pre-charge stage, and we'll have an evaluate stage. And then we'll pre-charge, and then we'll evaluate. And we just want to do this kind of alternating thing. Your logic is only going to be good during the evaluate stage. Does that make sense? Awesome. All right. This is basically a clock. Okay? So what we want to do is get something, a clock, to turn these on and off. Well, imagine I had my clock signal, and I want to charge, I want to connect to power when my clock is low. So I could come in here and put just one of those P gates back in. And I hook it to my clock. All right. Now, when clock is low, this will open and I'll be connected to voltage, so it will charge this. Does that make sense? Now, I took away N PMOS gates and I put one back in. So the relative size of this charging network compared to my original one, if there's N inputs, the size of this is 1/nth of what it was before. Right? Because you needed one transistor for each of your input lines. So this is just 1/n now. And in addition, that means this is proportionally much smaller. It doesn't have to go through cascades of that. So it's proportionally fairly fast. It'd be even faster if it was N, but then it couldn't switch power efficiently. So one gate is not too expensive to us. N gates, that's really expensive. So that's why this is a really good trade-off. Now, at this point, there's like a whole network here. So I can adjust the size of these so that when this is open, it overpowers this one and charges up even though this will drain away. All right. So I could just do it that way and just say, this is when it hooks it up. When it goes here, it disconnects. And so then this would be able to discharge it. All right. And I just have to make this able to supply more than this. Some systems do that. That is called a footless system. Right here, as drawn, this is called footless. No foot. The foot is the bottom. And I'll show you why it's footless in a sec. Right. So footless is my blue line here. Imagine I took and I replaced this and I stuck in another one here and I hooked this one to my clock. Now this is an NMOS. So this one opens up on a 1 and it closes on a 0. So during the 0 time, this disconnects ground. So nothing can flow through that pull-down network because the pull-down network is disconnected from ground. Which means I'm no longer fighting the pull-down network. I'm just charging. And then the second I reach the evaluate stage, this one disconnects and it connects the pull-down network. And remember, N's are really small and fast. Right? They're about a third the size, right? And 3 times as fast. So this is really cheap and easy to add in. But it's way at the bottom of this whole structure, so that's called the foot. So if you add in a foot, it's a footed system. If you don't use the foot and you just allow it to fight a little bit, it's a footless system. Does that make sense? Yeah. Sorry, the foot. It will be more efficient heat and power-wise and charge speed-wise unless all of the inputs can be guaranteed to be 0 during the pre-charge phase. If you could guarantee me that all of the inputs were 0 during the pre-charge phase, then it would be disconnected anyway. And your footless system is going to be actually more efficient than the footed system. Does that make sense? It turns out that you can actually guarantee the inputs are 0 at a particular time. Right? So there are times when you can guarantee that they're going to be 0, particularly when you start cascading these systems. Right? because you disconnect things and everything else, right? So there are times when they are. So sometimes on the interior of some of these network evaluations, it's efficient to remove the foot because you can logically prove there's no need for it. And so that just helps you all around. So the early systems were footless, and then they went, ooh, much more efficient with a foot, and then they went, ooh, depending on where it's located, do a little analysis, and sometimes you can get rid of the foot and keep the efficiency. In which case that foot is unnecessary, so it's actually a waste. So the footless system becomes more efficient. Does that make sense? Okay. So we've got this basic sequence here. Let's think about how it works, because this is kind of our key idea, right? So we've got this series of a pre-charge stage and an evaluate stage. So imagine I have this timing diagram that's going on. This is my clock. Okay? And you build your pull-down network just like you did before. You make your Kono map. Basically, anytime you want to drop those zeros in, you make sure this pulls it to ground. All right. So imagine that I'm on here, and I want to take a look at my output. Let me just call the output F here for a sec. So F is going to have evaluate times when you can look at it and times when you can't. It is a synchronous system. It just has no actual memory. So don't call it a true synchronous logic. Some people do call these synchronous because you have to time them. But synchronous is also used, if you remember, throughout digital logic design to mean with memory, right, as well as with a clock. So while it's technically true what they're saying, it's confusing as heck to anybody who's going in there. So it's just better to call it pre-charge, evaluate, or dynamic. And then you should just know, if anybody ever says dynamic, it means the signal's only good at certain times. So let's consider F's voltage. Without loss of generality, let me just assume that this was discharged at the start of my time, right? Just so I can kind of draw it. And remember, this is time progressing this direction. So I'm starting off and I'm low, so that capacitor is going to charge, right? And let's just say during this part of the phase here, just that the pull-down network is going to supply a zero, right? That it connects you to ground, but it'll only connect you to ground. We'll assume we have a foot here. It'll only connect me to ground when the clock is high. But just during this time period, I don't want to bother joining the network because it's kind of a waste of time. That's basically digital logic. All right? So let's say it's supplying a zero, which means once it gets to this point, this is gonna, it turns on, that zero comes in, and everything's gonna want to drain out. And it'll drain really fast because I've got a ground. So it goes, so there's a period when it reaches it. All right, so there's a little delay. From when the clock hits, there's a short delay to discharge the capacitor. We agree? And then we hit the next clock up cycle. There's a short delay till it gets up, but then it's on. It hits the next one, it's supplying a zero, bloop, down it goes. Hits the next up cycle, up it goes. All right, see how that's kind of working? All right, and that's just this one connects and charges it during the pre-charge phase. This one, right, that turns off, this one turns on, and it discharges. So this, you could read this legitimately anywhere inside these time periods, and you got to legit get your zero. And it is blindingly stupid fast. Okay. What happens if it now starts supplying a 1? All right. Supplies a 1. Well, when it comes here, right, I mean, and by that it means, or, you know, you could say Z really, right? I guess truly, right? Because it's not actually giving you a 1. It's just not connecting you to ground. Right? So this, during this period, effectively this PDN does not connect you to it. That means this capacitor is now supplying out here to the system. That outer system shouldn't be a heavy draw on it. If you design your logic right, and that's what we're trying to do here, it doesn't take a lot to do these. So I got to make sure this capacitance is sufficient to do it, but assuming it is, it's going to have a very slow drain. All right? So it is a downward curve, but it's kind of much different time constant because the system on it isn't really as demanding as this one was. So it's going to stay in the 1 zone. So it is dropping. It can't drop forever. Once it's going to get close to that region where it goes, that middle uncertain zone between the 0 and the 1, because usually you're a 1 if you're above like 2.4 volts, like assume a 5 volt scale. It'll give you a rough idea. The upper half is usually considered a 1. Right? 1 volt and below is usually considered a 0. When you drop to 3.3, usually you have a volt up and a volt at the bottom, and the in-between zone is who knows, right? So we just try to stay at, and that's safety-wise. So before it's going to drop to the point where you do it, you're going to have to recharge it. It'll do that really, really quick. If it keeps supplying a Z, it'll do that same slow drop. So it'll read a 1 over that whole time period. That make sense? All right, so clearly this works awesomely, but right now I've made the assumption that there's no change in the logic during the time you're reading it. Does that make sense? I've kept 0 constant, right? Your actual, this F, the inputs, which control F, right? There's been no change. So it works great when the inputs don't change during evaluate. What happens if the inputs change during evaluate? Not as horrible as you think, right? Let's assume, we'll just keep drawing this. I need a little more space here, right? So here's my clock again. All right, we're going to down here put our PDN, and it'll either give us a 0, meaning it gives us ground, or it'll, when I go up, it'll be Z. So it'll be 0 or Z as its value. All right? All right. Let's assume that we've been doing Z, so let's stick at Z. And then partway through, let me switch to 0 here. All right? And then we have our F. So here on F, right, it charges up during the pre-charge. When I go to the evaluate stage, it's still Z, so it's slowly discharging, right? It charges up during pre-charge. Initially, it's supplying Z, right? It's disconnecting me from ground, so I'm slowly discharging out through the system. And then all of a sudden, it connects me to ground. Whoosh. Right? So it gave me a 1, and when it transitioned, it went pretty quickly to 0, didn't it? And then the pre-charge is completely unaffected by any of this stuff. It charges back up again. And let's say I just went up again. We could get any point along here and drop it again, and it's going to slowly go. And then once it gets connected to ground, whack. Right? So it holds the 1 and it transitions to a 0 just like we would like it to. All right? So we've seen that if it stays 0, right? 0 all the way through the time period, that was good. 1 all the way through the time period, that was good. If it starts out a 1 and it goes to a 0, that's good. The only thing left is it starts a 0 and it goes to a 1. Does that work for me? So we need to start 0 and go to 1 partway through. All right, so we hit this, it charges up, and I'm ready. It sees ground, it discharges, and that sees the shift up, so it disconnects. This right here disconnects, so the capacitor is no longer being grounded. All right, so at this point, there's no more grounding. But does the capacitor have any charge? No. So I'd like to see it go up again, right? That's what I want. But there's no charge in it. So it's going to stay until it hits the next charge phase when it'll charge up. So I wanted to see this, right? That's a want. But I get this. That makes sense? So it cannot, right, give me a 0 to a 1. If it starts out grounding, it's going to ground it. The capacitor is discharged. It's got nothing in it to bring it back up again if it later all of a sudden gets disconnected. It's going to be like, yeah, nice try. Wait till I charge up again. Okay? So it cannot respond. Now, the majority of your gates in your pull-down network, if an input is 1 in general, it's generally going to tend to connect it, turn it on, right? Now, if I were to cascade these things, one of these to the next one, initially, this capacitor is charged, so it'll supply a 1, which means it'll discharge this, right? Or cause the next stage to discharge, and then it's all over with. It can't respond back again. And it pretty much always starts at that initial 1 until it draws off. Right? So I'm in deep trouble, right? I can't cascade these. So it does one really quick stage, and then I need to stop it. Now, there are a couple things I could do, right? Since it initially supplies me that killer drain me signal, right? I could also delay the next stage, right? If I delay the clock to it, I just put some Z system on, right? Just put a delay, some small circuit to slow it down. You'll be totally good, right? But you have to be really precise on your timing and hope it doesn't heat up and change the timing or things of that sort, right? But there are ones who do that kind of a delay onto it so that it doesn't cause that problem, and then they can daisy chain them. And they just require what's called monotonically increasing signals, right? Or monotonic signals throughout, right? You can go 0 to 0, 1 to 1, 1 to 0. You just can't go 0 to 1. We just call that monotonic, right? Monotonically decreasing, technically, right? But we're totally cool with that. We can put a delay in so that it doesn't see that discharge, so you can avoid some of the problems. The other thing that I could do besides the delay is what domino logic does. They just put an inverter, a static inverter on it. A static inverter is really small and it's really fast. It now creates a buffer between the two, and it basically makes it clean so this doesn't have a problem, which means you're always initially supplying that 0 and you've got a delay that takes care of it, right? So you don't do them. So you can cascade dominoes, which is just everything we've done here, just put an inverter between it. That's how you make domino logic. And then they can cascade one to the next as long as you want to go. They keep getting recharged back up. It's a very strong signal. It's stupidly fast. The inverter is only 1 P gate added in, right? So it's not a significant slowdown on us on that, but it avoids the one problem case. Right? And that's usually pretty much the best compromise, which is why everybody does that. But again, like I said, it's essentially this, right? You remove the pull-up network, you pull the pull-down. All you do to get a domino logic onto this thing is you put an inverter. Now it's a domino. And one domino feeds to the next, and they just keep triggering very, very fast. Usually only the first one needs a foot. Usually all the rest of them are footless. That's it. That's nutshell the idea behind dynamic logic. We feel good with this? Awesome. Well, we are at our time then. I'm happy to answer questions if people come up with them. But you now have the basis for CMOS logic, families, and design.